All right, we're going to start into chapter 2, and this is a huge jump mathematically for you guys. Welcome to varsity math. This is true AP Calc. Chapter 1, limits, is important, but this is where you earn your street credibility right here, is starting up with derivatives. So like I said, this is a big day. And if you notice, the derivative involves a limit, which is why we had to spend time on limits. What exactly is a derivative? That's a great question. Well, it's the whole first semester of our class is what it is. But a derivative is simply the slope of the tangent line to any curve at a given point. Most students can visualize the slope of a line because you did that in middle school. You know, it's the m in mx plus b. But you don't think of a curve having slopes, or a slope. But a curve does have slopes, except that the slope of a curve isn't constant. It's changing all the time. If you're right here, the slope is the same as the slope of that little green, and we call it a tangent line, a line that brushes past it. The slope of the curve right here is pretty much zero. It looks horizontal. The slope of the curve over here is like, maybe positive 3, positive 4, maybe positive 5, up 5 over 1. It's pretty steep. Here, the slope of the curve is negative, maybe negative a half. So the slope of a curve is always changing, and the derivative is a way to calculate that slope of a curve and to find also what we call a rate of change, which is very useful. All right, so there's the formula for the derivative of a function. And there are 4 ways to list the derivative. One way is right here. And you can see it looks like an apostrophe. I'm going to write it a little bit larger. The way we say that is f prime of x. F prime of x. The little apostrophe is the prime sign. You can also say y prime, because you know how y and f of x are the same, so those are interchangeable. There's 2 other ways to say the derivative, and they're going to become the ways that we normally use all the time. One of them is dy dx. It has the appearance of a fraction, dy over dx. It's actually read the derivative of y with respect to x. The derivative of y with respect to x. And the 4th way, a lot of college professors in particular just won't bother writing the y. They're like, it's y, I'm not writing it. They just say ddx. That way they can talk real fast. They're like ddx, ddx, ddx. Doesn't slow them down. And the y is understood to be there. All 4 of these things are absolutely identical. And so I'll make an effort to use them interchangeably so you get used to seeing them all. All right, the best way to learn about derivatives is just to start some example problems with your teacher. I'm going to warn you, this is going to be a bit of a rough level up, if you will, in your math life. So don't panic. Just let's go with the flow for a few questions. Hopefully it's going to make sense. All right, that's the game plan. We're only going to do 3 examples for today, just so that you're not completely overwhelmed with this. Here's example number 1. Okay, as you can see, this is a 4-part problem. And we're going to start out by making a little picture off to the side. I love my pictures. And f of x equals x squared plus 2, that's a parabola. It's an upward opening parabola, so I'm just going to draw a sketch of it. Nice, that looks beautiful. I said it was a sketch. And I'm going to pick a random point on the parabola. I'll make sure it's not the vertex, so you don't think it has to be. This is so random, it's just called x comma y. That's about as random a location as I can come up with. Except I'm not going to write the y. Instead, I'm going to write x comma x squared plus 2, because that is y after all, right? Y is the same thing as f of x. Yeah, that saves me a variable. All right, the less variables that we have, the easier our lives are. So, hooray for that. All right, now, what Gottfried Leibniz and Isaac Newton, who are the 2 guys who discovered calculus independently of each other, what they both did was they decided to move a short distance to the right, to this point. And they called that distance delta x. Remember, delta is the triangle. It means difference or change in. Half the textbooks use delta x, half the textbooks use h. Our textbook uses delta x, but I like to call that distance h. I like to go against the grain a little bit. And the reason why I don't like the delta x as well is because when you start getting these complex problems that we're about to see, and you're writing a whole bunch of x's and delta x's in parentheses, the x's and delta x's start to look alike and it gets kind of confusing. I found that the h is a little cleaner. So, okay. So if you move to the right a short distance called h, then the second point starts with x plus h instead of just x. So that's cool. And it ends with x plus h squared plus 2. I've been teaching this long enough to know that this is the point of the problem where I start to lose my first few students. And a lot of people are just too polite to admit that they're lost, so they smile at me and shake their heads up and down. I'm like, I don't know if they really understand this. So I want to make sure that everybody understands. So think about this. If you're on the parabola, like this point right here, let's say x was 1. If you're on the parabola and x is 1, you'd be the point 1, comma 3. Because you take the 1 and you plug it into here. Or let's say that you were at 10, comma something. Well, you would take the 10 and plug it in, square it, add 2, it'd be 10, comma 102. Well, what if it wasn't a 1 or a 10 or a 5? What if it was an x plus h? Wouldn't you take the x plus h and put it right here and square it and add a 2? Yes? Great. That's what I just did. So now you can see where that comes from. All right, hopefully that cleared it up a little bit. All right, let's move forward. Okay, I want the derivative or the tangent line, which are synonymous. The derivative is the slope of the tan line. A tangent line runs right through the point x comma y, in this case x comma x squared plus 2, kind of goes like that. That's the tan line. In college bookstores, you can find all these cool t-shirts and tank tops with calc jokes on them. It's like, hey, I'm good looking and smart at the same time because, you get the tank top and it says, check out my tan lines. And it's got this drawing I'm making right here on it. And people are like, oh, man, that's good. It's either geeky or it's really cool, depending on who you're trying to impress. But that's the tan line. Remember from geometry that tangents only touch the circle once? Here in calc, a tan line only touches the curve at one point, and it's called the point of tangency right here. So that's the tangent line, or tan line. It's cool to say tan line. And I'd love to know the slope of the tangent line because that would be the derivative and I'd be done. But you can't find the slope of a line if you only know 1 point on it. You need 2 points because that way you can do, y2 minus y1 over x2 minus x1 like you did in middle school. Rise over run. Change in y over change in x. I don't have the second point. So instead, I have to go with something else. And the something else is this line right here that goes through these 2 points. But it's really not the line I want. Since it hits 2 points, we call it the secant line. You may remember in geometry, a secant passes through a circle twice, where a tangent just brushes past and hits it at one place. So that's the secant line. And the secant line is okay, but I'm more like, meh. Where the tangent line, that's really where my desire is, man. That's what I want. That's my first choice. Okay, so since I can't always get what I want, I'll just go with what I can get, which is the slope of the secant line. All right, here goes. The slope of the secant line, like anything else, is going to be y2 minus y1 over x2 minus x1. It's just like middle school, but worse. Okay, so y2 right here, I'm going to have to FOIL that out on the fly. So it's a pair of x plus h's. So that'll make x squared plus 2xh plus h squared. Okay, so that's that. then there's a plus 2 at the end. Okay, that's y2 minus y1, which is just this x squared plus 2. Over x2, that's the x plus h, minus x1, which is just the x. I'll give it a parentheses even though it doesn't need it. Okay, so what happens is the secant slope, the slope of the line that I don't totally care about. It seems weird that I'm doing all this work for a line I don't totally care about, but yeah, you know, it's the best I have. This denominator is simply going to be h, because the x minus x will add up to 0, they'll cancel. Speaking of canceling, we're going to have some canceling up top as well. When I take this distributive minus through, I'm going to have minus x squared minus 2. And if you combine everything, you can see that x squared, negative x squared, they cancel. Positive 2, negative 2, they cancel. You're simply going to be left with these two items right here. 2xh plus h squared. I don't know if you noticed something about all that canceling. There were 6 items there and 4 of them canceled out. And the 2 that lived were the 2 that had h's on them. It's almost like you're on the Titanic and H is a lifeboat. If you don't have an H, you're going down. You have a canceling partner that's going to seek you out and destroy you. Oh, man. So since everything up top has an H, and everybody's doing it, everybody's got one, then I should be able to factor out an H. And I can. So when I rewrite that with an H factored out, I'll just have 2x plus h, no longer h squared because it's factor. All right, so that got rewritten. That's going to allow me to cancel out these h's. And the slope of the secant line will be 2x plus h. All right, cool. I got the slope of the secant. That's the good news. The bad news is I'm lukewarm about the secant line. I'm like, yeah, secant line's okay. I really want the slope of the tan line because the slope of the tan line is the slope of the actual curve. The slope of the secant line is not. So how can I go from slope of secant to slope of tangent? Well, here's what we noticed. And this is what Isaac Newton and Gottfried Leibniz noticed. Let's say that the second dot turned yellow, and it was like a bright glowing yellow dot. And you could slide it down the curve, down the parabola. Like to there. What would happen is the secant line wouldn't be as steep anymore. What that would do is it would shrink h down a little bit. You can see that h isn't as wide as it once was. And if you could make that yellow dot get all the way to the other red point, so that h was 0, the secant line would wibble, wobble, and swivel until it would become the tan line. Oh my gosh. And so to make that magical transition between secant and tangent slopes, all I have to do is shrink this h down to 0. Now, of course, I can't make h 0 because remember, there used to be an h in the denominator and I can't divide by 0. But I can take the limit, oh boy, here's chapter 1, as h approaches 0 of the secant slope, which I just found to be 2x plus h. Let me back up one slide to the derivative formula now and see if it makes a little more sense than it did a few moments ago. Remember that my h is the book's delta x. I had an h on the bottom. They didn't even show where they got this from, but this is f of x plus h. That's like y2 minus y1 over x2 minus x1, which just turned out to be h or delta x because the x is canceled. And it's the limit as h approaches 0. They're doing exactly what I'm showing you on my picture, except the book didn't give you a picture. But this is what the derivative is. And the derivative is the slope of the tan line. Yeah. All right, hopefully it's starting to take shape. Let's go back to the problem that we're on, number 1. I don't know if you've noticed this about life, but man, life sometimes can be fickle. Take H, for example. Up there, H was like the lifeboat on the Titanic. If you don't have one, you're going down. H is like, your saving grace. And now down here, just a couple steps later, I'm like, kill off all the H's, make them all zeros. It's like a bomb drops on them. You go from the hero to the villain in like no time at all. But hey, such is life. So the slope of the tan line is going to end up just being 2x. And that 2x has a name, and it's called the derivative. Great. All right, we found our very first derivative ever. The bad news is this number 1 was a 4-part problem, and we haven't answered any of the 4 parts yet after all this work. It's so bad. Oh, geez. All right, I'm going to clear off some of my work so that we have space. All right, here comes the good news. This parabola goes through x equals 1, and we already saw that if you plug the 1 in, it's really the point 1, 3. So I know that 1.3 is where this dot is right here. It's the point of tangency. So that's kind of cool. I also know that 1 is the x and 3 is the y, so the 1 can come down here and get plugged into where the x is. So part A says find the slope of the curve at the point 1, 3, the indicated point. That's easy. That's the slope of the tan line there, the derivative. It's going to be 2 times 1, which is 2. All that work just to get that 2. All right, this process is going to get sped up quite a bit now. Part B and C can go together very nicely if you use point slope form. I know slope-intercept form is wonderful for middle school when you're graphing y equals mx plus b and graphing a bunch of lines. But in calc, it's not nearly as helpful. When I first learned point slope form, I thought, this is dumb. I'll never use this. And now I use it exclusively. It's like the best. So you'll buy in eventually if you're not going to buy in today. Don't you worry. What's great is since I know that the point 1, 3 goes through the parabola, and obviously it has to go through the tan line and the normal line as well, I can use the point slope form and just put in the 1, 3. Remember, 3 is the y, 1 is the x. And because I'm using point slope, I don't have to reinvent the wheel for the normal line. I can use the same point. It gets better. I know that the slope at that point is 2 because of part A, so this 2 can go right in here, and now I've got the answer to part B. That's the tan line. And the normal line is just perpendicular to the tangent line. It still goes through the point 1, 3, still goes through the point of tangency, but the normal line will look like this and make a right angle with it. So therefore, the slope is just the opposite reciprocal, so -1/2. So that's parts A, B, and C. And now part D says, draw a graph showing all 3 lines and curves. I'm going to do that on green globs. Okay, I graphed the original equation, y equals x squared plus 2. You can see that it does go through the point 1, 3. And when I type in my tan line, it should slide right past. It should just barely touch that parabola. Right at the point 1, 3, it's going to clip it. And that's the only place it's going to touch. Oh, look at that. Dead on. It's like a direct hit. Missiles don't know where they're going. They're just big hunks of metal with explosives inside. It's all programmed by math, by calc. Now, obviously, there's peacetime applications as well that help mankind. That's just an example. So that's the tan line. And, of course, the normal line will also go through the point 1, 3. That's why it's nice we don't have to fumble around with changing the parentheses. We'll just change the slope to -1/2. And voila, right through the same point, forming a perfect right angle right there. There you go. That's part D. All 3 have been graphed. Great job, everybody. We've done the first example. All right. We're going to pick up the pace a little bit now. We're going to go a little faster. I think you'll get into a nice rhythm, a nice groove here as we go. All right, this time it's a cubic. Again, most cubic graphs look like the letter S on its side. I'll pick a random point on here. I'll just call it x comma y, but it's not x comma y. It's x comma this, because that is y. It's f of x. Now, what would I do if I was Isaac Newton or Gottfried Leibniz? Well, I'd go a short distance to the right, called h, meaning that my new point starts with x plus h, and the x plus h gets put in for where the x's used to be. All right. Now I have to find the slope of the line that I don't really care about, the secant line, which again is that line right there. But really the one I'm hoping for is the tan line, the line that just barely cuts past that dot right there, the point of tangency. The tan line is the one I want, but the secant line is the one I have to settle for, because it's the one that has 2 points that I know. All right, here we go. y2 minus y1. This is going to be a treat. I'm going to have to cube this. I will cube it quickly. It's going to be x to the third plus 3x squared h plus 3x h squared plus h cubed. Whew! That sure beats writing out 3 parentheses and doing a whole bunch of FOILs. How did I get that so quickly? Pascal's triangle. I went to the third line of Pascal's triangle. Here's Pascal's triangle, pair of ones, that's line 1. Pascal's triangle always starts and ends with ones, but then to get the other numbers, you add. 1 plus 1 is 2. And you go diagonally down. So 1 plus 2 is 3. 2 plus 1 is this 3, and so on and so forth. You can see if I put ones on these as coefficients, I have 1, 3, 3, 1, which is this line of the triangle. The x's start out high and mighty at third power. They start losing steam, so it's x squared, x to the first, until the x's go extinct. And the h's rise out of nowhere to take control of the world. Here you have h to the 0, not even written, h to the first, second, and finally h to the third. So again, you can multiply things really quickly if you know Pascal's triangle and this thing we call the binomial theorem, which is what I used. All right, anyways, that's algebra 2, so back to calc. We've already seen what x plus h squared is. It's x squared plus 2xh plus h squared, but now I have to multiply it through by -4, so it's going to be minus 4x squared, minus 8xh, minus 4h squared. And then obviously we have this plus 11. Okay, that whole disaster is y2. It's just like middle school, but worse. If you had to do all that work in middle school to find y2, I think kids would have dropped out of school. Oh man, y2 minus y1. I'll tell you what, with your permission, since we're going to be subtracting this away, and it's a trinomial and I have to distribute, just to save a little time and effort, why don't I just copy it down, but I'll just change the signs on the fly, if that's cool. So I will do that. So y2, which is in parentheses, minus y1, so that'll be minus x to the third, negative x to the third, plus 4x squared, minus 11. So again, I just wrote this, but just changed the signs on the fly. Over x2 minus x1, which is just this, minus the x. The x's will cancel. It'll simply be an h, as always. Okay, let's see what can cancel. If you do not have an h, you're going down. You have a canceling partner. This plus 11, there's a minus 11 right below it. Negative x to the third. Where's the positive x to the third? Oh, right in the beginning. And here's a 4x squared without the h's. Where's the negative 4x squared? There you are. You cannot hide. Everything that survived has an h. If you do not have an h, you should have been canceled away. So it's nice. There's like almost like a checkpoint in the middle of the problem, for your safety. Since they all have h's, you can factor out an h, leaving you with 3x squared plus 3xh plus h squared minus 8x. I'm running out of room. Minus 4h. I'll put that up here. Again, still all over this h that's patiently waiting on the bottom. Although the h in the numerator can cancel that h in the denominator now, safely. So you can see what we're left with up top. And this whole thing I've been doing so far is the slope of the secant line, which is the line I don't totally care about. But that's okay. Now to make the transition, I have to create some room for myself. All right, that's the slope of the secant line, but I don't want that. I want my tan line. How do I get from the slope of the secant to the slope of the tangent? Easy. I channel my inner chapter 1 and I evoke a limit. And it's the limit as h approaches 0. Hey, to be honest, man, I wanted to do this limit the whole time, but I couldn't because I had a stupid h on the bottom. I just divided by 0. Once this canceling happened, game on. So this stuff all gets dumped into here. I think I'm just going to be lazy and not write it twice. But if you have an h, you are now gone. Because if h is 0, you're going to get stuff like negative 4 times 0. Boom. 0 squared. 3 times x times 0. That's gone. So the slope of the tan line is going to be what's left over, which is 3x squared minus 8x. And that is yet another derivative. There's your second derivative you've taken so far. All right, 2 derivatives under our belt. 2 down, many to go. All right, we have to answer the 4 parts. Part A, find the slope of the curve at the indicated point. What indicated point? Oh, x equals 3. There we go. So we'll take a 3 down there. We'll plug a 3 in. That's going to give me 3 times 3 times 3. That's 27 minus 24. That's 3. So the slope of the tan line up here, the answer to part A, is going to be 3. That's the slope of the curve when x is 3. By the way, these normally don't match each other. That happens like 1 time out of every 100. So don't think, that's going to be normal. That's just coincidental here. Let's see where we are on the curve. If we plug a 3 in, let's see what the y-coordinate comes out to be. Again, 3 times 3 times 3, that's 27, minus 4 times 9, that's 36, plus 11, that's negative 9 plus 11, that's going to be 2. All right, so we're at the point 3, 2. So this S curve goes through 3, 2. We need to make the tan line, the normal line, and we'll graph all 3 of them on green globs. And that'll be it. I originally said we're going to do 3 problems today. Let's make it 2. We're going to quit right after this one. It'll be time. The great thing about this is the 0.32 can be totally utilized. Remember that the 3 is the x. The 2 is the y. And of course, you always go opposite signs whenever you're doing point slope form. The normal line gets the same 3, 2 put in. And then finally, the slope, well, it's just 3. It's the answer to part A. And if the tan line has a slope of 3 at the 0.32, then the normal line is going to have a slope of negative 1/3, the opposite reciprocal. So there are your 3 answers. All I have to do now is just graph all 3 and we'll be done. All right, there's the original graph. There's the 0.32 that we promised it would go through. So far, so good. And now I'm going to go ahead and put my 2 lines on. First, the tan line that hopefully is going to kind of shoot right past here and just clip it at this one spot only. Now, remember that I said that the tangent line only hits the curve once. That's in the immediate area. Eventually, it's going to come down here, and the red line, the red curve being so steep, they are going to cross again. anytime you get problems where you start getting cube, fourth, fifth powers and they grow, the lines or the curves are so curvy that a tan line will cross more than once. But we're always referring to the immediate vicinity of the 0.32 that it only hits once. Okay, so hopefully that clears that up. Okay, I typed in the tan line. Let's see if it does what I hope it does. Oh yeah, look at that, it's perfect. And then finally, almost anticlimatically, the normal line has a slope of negative 1/3. Of course, it's going to go through the 0.32 because I didn't change the parentheses, but it does make a nice right angle with the green. So there you are. All right, that concludes day 1 of section 2.1. As you can see, a big step up. We learned how to do a derivative, take a derivative. We're graphing tangent and normal lines, and we're starting to make the lines behave the way we want them to. We're sort of being able to start to control graphs, which gives you a small insight to how difficult it is to make, decent video games. Can you imagine some of the math behind the most recent stuff? I mean, when I was in high school, we had like Breakout and Pong, where you had it was almost like you're like a hockey goalie. And now, you've got virtual reality going. I can't even imagine the math behind that stuff. So, obviously baby steps here, but we're getting there. All right. I'll see you guys for day 2. Until then, take it easy.